Good afternoon, sir. Am I audible? Good afternoon, ma'am.
Good afternoon, everyone. Welcome to the final day of a faculty development program on deep learning and computer vision in the field of clinical research. Over the past 5 days, we have explored deep learning architectures, AI-driven clinical diagnostics, optimization techniques, and computer vision applications. Each session has given us deeper perspective into how AI is revolutionizing healthcare and biomedical image analysis. As we conclude this enriching journey, today's sessions will cover sequence modeling, optical flow techniques, and computer vision for brain imaging, providing a well-rounded perspective on AI's evolving role in medical technology. So we begin the final day session with Dr. Malayanath Kumar sir, who will be leading this session on sequence modeling using recurrent neural networks. As we have already been introduced to him in day 5, we are excited to continue learning from his expertise. This session will focus on how RNN are used to model sequential data, especially in medical series analysis, predictive healthcare systems, and bioinformatics. Over to you, sir.
Thank you, ma'am. So let me allow to share my screen. Is my screen visible, madam? Madam, is my screen visible?
Yes, sir. Yeah, it's visible.
Yeah, fine. Good afternoon to all. So as we have discussed in yesterday's session that we are talking about the recurrent neural network, LSTM and GRU. So already you have one brief idea that what exactly the recurrent neural network and how exactly the recurrent neural network works. So just a quick review within 2 to 3 minutes that we are talking about this recurrent neural network. And this recurrent neural network basically works on the principle of the hidden state or the contextual information. So it based on the contextual information, it can provide the output that what is the output based on the previous or the past hidden state informations. So in this case, we have discussed that this recurrent neural network is consist of one input layer, one output layer, another is called the hidden state. And it will represent this information that will represent it like unrolled version of the RNN, where the each layer is having a input as well as the output as well as the hidden state. And this hidden state information passed into the next hidden state to provide the output. And this output depends upon the previous hidden state information and the current input. Here we have discussed that there are 3 weights are present. One is called the U, which lies between the input layer to the hidden layer. That is nothing but the weights with the input to the hidden, and W hidden to hidden, and V which represent the weight that is associated with the hidden to the output layer. This information that already we have discussed in yesterday, and we have seen that how the back propagation through time is possible in case of this recurrent neural network, and we can able to get the output. And already we have discussed that when we are going for the back propagation, so basically we are calculating the final loss as well as which is represent the loss over the complete time series, and final gradient, that is the sum of a gradient over all the time steps. And as we are computing these values, this gradient is calculated with respect to W. This gradient is calculated with respect to V and with respect to U. And this information already we have discussed. And in this case, we are applying the chain rule to compute this loss with respect to the different weights. I hope this is clear. So what the next important information that we have discussed, in this case there is a problem occurs that is called your vanishing gradient as well as exploding gradient problem. But this vanishing gradient, this problem is very serious, and in order to overcome that type of limitations, so we are going for this LSTM network as well as the GRU network. So if we have that means a deep recurrent neural network which is having 50 number of layers, basically in order to update the weights, we are back propagating through time. That means back propagate to H0. What is H0? H0 is nothing but the hidden state information at the 0th layer. H1 is the hidden state information at the first layers like H50, that is the hidden state information at the 50th layer. So when we are doing the back propagation, we are calculating the derivative with respect to, or the loss with respect to y with respect to h with respect to the previous h, and this process will continue till to the h0 and del h0 by del w we are calculating. So when we are calculating the gradient, basically we are calculating with respect to the tan hyperbolic x, and generally we know that the derivative of tan h is bounded, that is 0 to 1. So if this 0 to 1, that means the derivative is a value lying between 0 to 1. So when it is multiplied with another smaller value, it will lead to another smaller value. So after certain number of layers, this gradient will become very, very small, and the recurrent neural network can not able to learn, and this is known as the vanishing gradient problem. Similarly, the reverse operation is nothing but the exploding gradient, in which this leads to, or the gradient will lead to infinite. And in order to overcome that type of difficulty, people have thought of the gradient clipping, that is known as how we can able to clip the gradient by the help of a normalization, which represent a threshold with respect to the gradient normalized. That means with respect to the gradient multiplied with this gradient. So this information that we have discussed, and we have discussed one of the application of this recurrent neural network, that how to generate the music, and we have discussed the various types of recurrent neural network, that is one-to-one, one-to-many, many-to-one, as well as many-to-many. So these are the few of this network that we have discussed in last class. So now we are talking about the bidirectional RNN, or where exactly we have stopped yesterday due to the internet issues. So what is this bidirectional RNN? This bidirectional RNN is consist of two different layers. That means if we look into this architecture, then we can see that there is one set of layer which is passing from past to time steps, and another set of layer from future time steps. So that means how exactly it is represented. It consists of two different layers and connected from input to the output. One is from left to right and another is from the right to left. So there are the two set of values of this layer. One is called your forward hidden layer information. That means the hidden state values are stored from past time state. What is past time state? So H0 is the past and H1 is the current. When H1 is the past, H2 is the current. So when H2 is the past, H3. So this is called past time step. That is H0 to H1, H1 to H2, H2 to H3. That means H3 information or H3 depends upon H2, H2 depends upon H1, and H1 depends upon H0. This is called past time step. And what is the backward hidden layer? The backward hidden layer that consists of the hidden state values from the future time step. So what exactly it is? It is nothing but Z3 to Z2, Z2 to Z1, and Z1 to Z0. So that means it has a two pass. One is called forward pass and another is called your backward pass. So which is clearly represented in this diagram. I hope it is clear to everyone. So now how exactly this can be represented? This can be represented in another form, which is consist of the different LSTMs in the forward pass as well as the LSTMs in the backward pass. So if you look into the three-layer architecture where there are three layers are present, one is xt and the previous layer x of t minus 1, and the next layer that is equal to x of t plus 1. So now this each layer has an output that is y of t minus 1, yt, and y of t plus 1. So in the forward pass, it consists of a LSTM that will be coming from h0 or the h of t minus 1 to ht, next h of t plus 1. There is a backward pass of LSTM that is coming from h of t plus 1 to h of t and h of t minus 1. And this is the architecture of this bidirectional LSTM, that how exactly it is present. So now we'll just see how where we can able to use the bidirectional recurrent neural network. So this bidirectional recurrent neural network can be used when we require certain information in the past from the future. Just we'll take one example of this. Suppose I will utter the sentence that is Dr. Vijayalakshmi lived for 20 years in Vyas. So she is good at speaking Tamil. So if we look into the second statement, this she is good at speaking Tamil. That means as she is very fluent in Tamil, so there is a huge chance or the probability or the prediction is that she lived in Tamil Nadu, or that means she has lived in Tamil Nadu. That's why say fluent in Tamil. So in this case, the blank can be filled by looking into the information on the future. So the future can able to predict this past information. So that's why this bidirectional LSTM is very, very important. So we can say that In case of simple RNN, this cannot be filled, because in case of simple RNN, we are talking about Dr. Vijalakshmi lived for 20 years. What is the past information? The past information is this. In recurrent neural network, this blank cannot be filled by simply looking into the Dr. Vijalakshmi lived for 20 years in DAS. So RNN cannot fill the blank. RNN can make predictions based only on the words it has seen so far. So that means if we look into the past statement, the RNN can able to see the words up to this. So that means from doctor to in. So based on this, it cannot able to fit. So Dr. Vijalakshmi lived for 20 years in will not provide much information about the blank. So she is good at speaking in Tamil. When this statement is there, then it will can be retrieve the information that she lived in Tamil Nadu. So in bidirectional recurrent neural network, however, this online setting or suitable for online setting where we don't know the futures, this may not able to work. So now we'll take this forward hidden layer. What is this forward hidden layer? Already we have discussed HT, that is equal to softmax of UH. What is UH? UH is nothing but the weight that is associated with the input to the hidden layer. And XT is nothing but the input at the current time state, that is equal to T. W is nothing but the weight that is associated with the hidden layer to the hidden layer, and H of T minus 1 is nothing but the hidden state information at the time step T minus 1. So this is the information that is called forward hidden layer information that will be represented by softmax U of H XT plus W of H T minus 1. In case of a backward hidden layer, so what will happen? We are taking or calculating the ZT. What is ZT? ZT is nothing but the softmax of UZ What is this UZ is nothing but in the weight that is associated with the input to the hidden layer, and XT is nothing but the input that is associated with the layer that is equal to T, and WZ is nothing but the weight associated with the hidden layer to the hidden layer, and Z of T plus 1, that is nothing but the information that is called associated with the hidden layer. So now, what will be the net output in case of a bidirectional recurrent neural network? The bidirectional recurrent neural network, this predicted output can be obtained by softmax VHHT, VZZT. What is VH? VH is nothing but the weight that is associated with the hidden layer to the output, and VZ is also associated with the weight that is called the hidden layer to the output in the one is called forward direction, another is called the reverse or the backward directions. So if you recall your memory, in case of yesterday's class, we have discussed in session, you have discussed softmax of VHHT. But now in case of bidirectional recurrent neural network, this is nothing but the summation of VHHT plus VZZT. So in case of a bidirectional recurrent neural network, we are having the two passes. One is called forward pass, another is called the backward pass. That already we have discussed. So now, what are the pros and cons of this bidirectional LSTM? Because this will give rise to the LSTM network. We'll talk about LSTM just after a few minutes. So if you look into the pros and cons of a bi-LSTM, it captures a long-term dependencies. It has a improved performances. It can perform better than the traditional LSTM. We'll talk about LSTM today. That what is LSTM? What are the limitations of the recurrent neural network that we are going for this LSTM? And these LSTMs are very popular in case of speech recognition, machine translation, as well as the time series data. That means analysis of the time series data, like this ECG signal, EEG signals, where the informations are depends upon the past informations. And this bidirectional LSTM is flexible in architecture. That means it can be customized by adding additional number of layers, such as convolution, attention layers, which can able to provide the improved performances. If we look into the other side of this bidirectional LSTM, it has a high computational cost because it is a move in both the directions, that is forward and backward direction. It requires a large amount of data, that is more training time. Without sufficient training data, the model may overfit the training set and fail to generalize the new set of data. And it will behaves like a black box. And in order to overcome that black box issues, researchers have used for the explainability or the explainable AI, which provides the explainability as well as the interpretability, and which basically gives a trust about the model. So now we'll talk about what is this LSTM. What exactly the problem happens in the recurrent neural network. In case of recurrent neural network, the problem that is happened, it fails to retain memory for a longer time. If you have a some sentence of a very long time, then it cannot able to predict what will be the next output, because it cannot able to keep the memory for a long time or a long sequence. Or in other words, we can say that for a long sequence the information cannot be retained. That means the recurrent neural network cannot able to retain the information for a longer period of time, and it has a problem of that is called vanishing gradient. So in order to overcome these limitations, that means in order to overcome the limitations of the memory as well as the vanishing gradient problems, this long short-term memory network has been developed. So what is this long short-term memory network? Basically, this long short-term memory network is having a structure that is known as the gate, and which keeps the memory for a longer period of time. So how it will keep the memory for a longer period of time? The very simple example is that whatever the information is required, that has to be kept. Whatever the information is not required, that has to be deleted or removed or eliminated. So this principle is used in case of LSTM network to keep a longer sequence of memory. And there is another solution to this recurrent neural network that is known as the GRU, popularly known as gated recurrent unit. In case of LSTM, it has a multiple number of layers, input layer, forget layer, output layer. So instead of there are multiple gates are present. So in case of gated recurrent unit, it will become a simplified version of the LSTM. It can learn both in the forward as well as the backward direction. It provides, there are other architectures, sequence to sequence model also people are using. Maps input of varying length to output of varying length. And the architectures that is used in case of sequence to sequence or the attention model. So what we'll discuss in this session, we'll talk about the LSTM, what is this LSTM, how LSTM can able to overcome the limitations of this recurrent neural network, how we can able to perform the forward as well as the backward propagation in LSTM, as well as the GRU. We'll talk about GRU as well as the deep recurrent neural network. Now we'll come to the same example. Yesterday we have discussed. The sky is dash. In case of recurrent neural network, we can able to predict the sky is blue. That means a recurrent neural network can easily predict this blank or the blank line can be filled by the recurrent neural network, which is nothing but the blue, because it works on the principle of the previous hidden state. So the recurrent can cover, but it cannot able to cover a long-term dependency. What is long-term dependency? We'll just understand this by the help of an example of the long-term dependencies. Suppose I'll utter the word, Dr. Vijayalakshmi was born in Tamil Nadu and she lived there for 10 years. She loved cooking. She is a fan of movies. She is fluent in dash. So now, in this case, it is a very big statement. I have written Dr. Vijayalakshmi was born in Tamil Nadu and lived for there 10 years. She loved cooking. She is a fan of movies. She is fluent in dash. That means this information is basically depends upon the past statement, that is Dr. Vijayalakshmi was born in Tamil Nadu and lived there for 10 years. So now, as she born in Tamil Nadu and lived for 10 years, this information can able to predict what will be the blank statement, blank line. So now she is fluent in Tamil. So this missing word is nothing but the Tamil. So it can, so this LSTM can able to keep, or it can able to keep the memory for a longer dependency. It can able to keep. So fluent in Tamil. So what is the missing word? So I can say that Tamil. So how it can be predicted? This can be predicted on the past statement. But she loved cooking. She is a fan of movies. These two lines or these two statements doesn't provide any information about this blank statement. So by remembering the previous information for a longer period of time, we can able to predict what will be the output in case in of this case. So by remembering this previous sentence, it understood that Dr. Vijayalakshmi was born in Tamil Nadu and lived there for 10 years. And this statement helps in predicting the output, that is nothing but the Tamil. But in case of recurrent neural network, it cannot able to keep such a long sequence of informations. This long sequence of information cannot be kept in case of a recurrent neural network due to the problem that is known as the vanishing gradient. As we are back propagating, so this gradient will become smaller and smaller. That means at certain point of time, it will become infinitely small or a very small number, which cannot be predicted. So this variant of recurrent neural network that is known as the LSTM can able to solve the issues. So what makes this LSTM network to understand or to keep a longer sequence in past, or what makes the LSTM cell to be special and different from this recurrent neural network? How does this LSTM cell can achieve the long-term dependencies? How it can be possible in case of long-term dependencies? How does it know that information to keep and what information to discard? That means which information we have to discard, which information we have to keep, and how it can be predicted. This can be achieved by a special structure that is known as the gates. So the most important part in case of a LSTM is known as the gates. What are these gates? These gates are of in LSTM are known as the input gate, output gate, as well as forget gate. So we'll discuss about each and individual gate and their importance in case of LSTM to decide or to predict the blank. So what is the responsibility of these gates? This is responsibility of the gate to decide what information to be added, what information to be forgot, and what information to be kept in the memory. So there are three types of gates in LSTM. One is called the input gate, output gate, as well as forget gate. Forget gate is basically responsible to forget the memory, to remove or to eliminate certain information from the memory. That means the information which is not required, that has to be eliminated. Now, input gate basically responsible for adding new information to this recurrent neural network or this LSTM. So this is basically provides the additions. Now, output gate provides the output. That means what will be the output of this LSTM network. We'll talk about each and every gate and how these gates are basically working. So what information to add, output, and forget from this memory of this LSTM, that will be decided by these three gates and effectively keeps the information in the memory for a longer period of time. So what are these gates? Now just look at this diagram. In this case, there are two states are present. One is called the previous hidden state, which is represented by h of t minus 1. Now there is a next state that is known as the h of t. So t stands for the time state. So t minus 1, the previous time step, t is nothing but the next time step. Now there is an input which is given to the xt. Here I have taken a simple LSTM network. There are multiple number of LSTM networks can be connected. So a simple LSTM consists of this forget gate, input gate, and output gate. Now what this forget gate is connected? This forget gate is connected to the xt, and the output is connected to the state, or that is equal to c of t minus 1, that is previous cell state, and the cell state of the next time test. And we will discuss what is the importance of this cell state in case of this LSTM network and how it will help to predict the output in case of the LSTM networks. So as we are talking about this recurrent neural network, which use a hidden state, and it is for storing the information and making the predictions. Basically, this recurrent neural network is use the hidden state to store the information and prediction. But what about the LSTM? This LSTM has a hidden state and which is broken into two states. One is called the cell state and another is hidden state. But in case of recurrent neural network, only hidden state is present. In LSTM, there are two is present. One is called the cell state and hidden state. What is the importance of the cell state? It is the known as the internal memory where all the information will be stored. Basically, this helps in storing all the information that is known as the cell state. Now, what is called the hidden state? It is used for computing the output. So now the cell state and hidden states are shared across every time steps to generate the output. So now in case of recurrent neural network, only hidden state is present, whereas in LSTM network, there is a cell state and hidden state is present. This cell state is basically known as the internal memory and keeps the information, and the hidden state basically produced or predict the output. Now we'll just look into the different gates. Already we have discussed there are three gates are present. What are the three gates? One is called the input gate, output gate, and forget gate. We'll discuss about each and individual gate's importance in case of the LSTM network. The first gate is called forget gate. The forget gate, as the name says, forget, that means to remove, to eliminate, to forget the things. So that means the LSTM network will help to eliminate the informations. How it can able to eliminate the information or remove the information of a cell state or from the memory. Now we'll just take this example and we'll understand this by the help of this example. Suppose I will say Pungrali is a good singer. She lives in USA. Vijayalakshmi is also a good singer. The moment I'm talking about, sorry, the moment I have started discussing about Vijayalakshmi, the Pungrali information is no more required. Just try to understand. Pungrali is a good singer. She lives in the USA. Up to this point, the information about Pungrali is present. The moment I am starting about Vijalakshmi is a good singer, or the moment I have started or uttered the word Vijalakshmi is a good singer, that means I have deleted or removed the information about the Pungrali. So that means I can say that the moment we started discussing about Vijalakshmi, the subject Pungrali, to Vijalakshmi, the Pungrali information no more is essential. This need not to be stored in the memory. This forget get will decide that which information has to be stored in the memory and which information has to be eliminated or removed or forget. So in this example, the information about the Pungrali has to be removed. That means the forget get remove the information about Pungrali from the cell state. Now, what will be the output of the forget get? The output of the forget get will be 0 or 1. If it is 0, the information has to be removed. If it is 1, the information has to be intact or it has to be kept. So how it can be possible in case of this LSTM network by the help of this forget get? So in this case, we are having a weight that is associated with the input to the hidden state. So now there is nothing but another weight that is associated with that is W of F with associated with the previous weight. So based on this, we can able to calculate what is the output of the forget get. So what will be the output of the forget get? The output of the forget get can be represented as the sigmoid of UFXT. What is UF? UF is nothing but the weight that is associated with the forget get, that is from input to the hidden state. So U is stand for input to the hidden state. F is stand for associated with the forget get. XT is nothing but the input, the associated at the time state that is equal to T. What is WF? W is nothing but the weight that is associated with the hidden state to hidden state. F represent that is corresponding to the forget get. H of T minus 1, that is nothing but the previous state information, that is called H of T minus 1. And what is BF? BF is nothing but the bias that is associated with the forget get. So the expression for the forget get can be represented as sigmoid or of U of xt plus W of H of T minus 1 plus BF. So when Ft is equal to 0, that means the information has to be forgotten, or that means information has to be removed. And when Ft is equal to 1, this information has to be intact or it has to be kept. So it is already represented here. What is UF and what is WF and what is BF, that is known as the bias. Now we'll come to the next get, that is called your input get. What is input get? What is the work or responsibility of the input get? This input get decides about the information that has to be stored in the cell state. So it is basically responsible for deciding about the information, what has to be stored, what has to be kept in the cell state. So now we'll take the example of the same, that Pungrali is a good singer. She lives in the USA. Vijalakshmi is also a good singer. So that means till I am discussing about the Pungrali is a good singer, she lives in the USA, I am discussing about the information about Pungrali. So the moment I have discussed about Vijalakshmi is also a good singer, I have to forget the information about the Pungrali. And the moment I have started Vijalakshmi, this information has to be added into the cell state. So what the information has to be added? The information which has to be added in the cell state, that is nothing but the Vijalakshmi is a good singer. So that means after the forget get, eliminate the information from the cell state, the input get will decide that what information has to be kept in the memory or which information has to be passed into the memory. So this input get will decide that which information has to be passed into the memory. So the same way it is represented, Pungrali is removed from the cell state by the forget get, and the input get will decide to update the cell state with the information about the Vijalakshmi. So now, what is the output of the input get? The output of the input get can be controlled by a sigmoid function. That means if the output is equal to 0, not to be stored in the information, that has to be removed. If 1 is the output of this, then this information has to be stored. Now we'll just understand the mathematical representation of the input get expression. What is the input get expression? The input get expression can be represented as IT, that is equal to sigmoid transfer sigmoid u of I xt w I h of t minus 1 bi. What is u? U is nothing but the weight that is associated with the input to the hidden state. As I represent, that is nothing but the corresponding to input to get, and xt is nothing but the input that is associated with the tth layer. Wi, that is the weight associated with the hidden to hidden state of the, or hidden to hidden layer weight, and the I stand for the input get. H of t minus 1, the previous hidden state information. Bi is nothing but the bias that is associated with the input get. So IT basically nothing but provides the output or the information which has to be added into the cell state. So we have discussed two states, two gets. One is forget get, which basically helps to remove the information from the cell state. Another is called the input get, which basically tells which information to be added into the cell state. So there are two gets information that we have discussed. One is called the input get, another is called the forget get. Now we'll just look into the output get, which is the third get. What is this output get? This output get will decide that what will be the output of this cell state, or it decides the information that should be taken from the cell state to provide the output. That means the output get will take the information from the cell state and it will generate what will be the predicted output, or the output in this case. So here I have taken one example. Dr. Vijayalakshmi published a paper which was a great success. Now here I have taken the second line, that is congrats dash. That is the blank statement is here. So now the congrats dash. So this or the blank statement will be filled by congrats Vijayalakshmi, because this represent to the Vijayalakshmi. So I can say Dr. Vijayalakshmi published a paper, was a great success, and congrats Vijayalakshmi. So now the output get will look up the information of the cell state and select the correct information that has to be filled in the blank. So the correct information that has to be filled in the blank is nothing but the Vijayalakshmi. So congrats Vijayalakshmi. So this is the output get will decide the output based on the cell state. That means what will be the output of this output get. So how we can represent the output get expression? The output get expression can be represented by OT, that is equal to nothing but the sigmoid of OT xt WO h of t minus 1 BO. So what is this U? This U represent the weight that is associated with the input to the hidden state. O stand for the output get. Xt basically represent the input that is associated with the time state, that is equal to T. WO is nothing but the hidden state to the hidden state weight. H of t minus 1 is nothing but the hidden state information that is associated at the time step t minus 1, and B0 is nothing but the bias that is associated with the output get. So the output get it will be represented by OT, that is equal to sigmoid of U of O xt plus W of O H of t minus 1 plus BO. So here three gets have been discussed. One is the forget get, to forget the information. Another is called the input get, what information is to be added into the cell state. Output get, which basically provides the prediction of the predicted output from the cell state. So three gates we have discussed. And if we look into the representation of the three gates, all the gates are having the similar kind of representations, and which is associated with some weights, that is nothing but U and W, where U represent the input to the hidden state weight and W represent to the hidden state information. And each of these gate is associated with the input, that is nothing but the input associated with the time state. And this hidden state to hidden state information is multiplied with the previous hidden state information, that is h of t minus 1. And each of this gate is associated with a bias that is called BF or BI or BO. So these representations are very easy to remember, that how exactly the correlation is present in case of forget get, input get, and output get. Now the question is how to update the cell state informations. This is a very crucial aspect, that how to update this cell state information. So now, how we can actually update the cell state by adding a relevant or that is new information uh, and deleting the informations. So, am I audible? Yes. So how we can actually update the cell state by adding a relevant or that is known as the new information and deleting the information which is not required from the cell state with the help of the gates. So here we are adding one information that is known as the cell state. We are adding a new relevant information by the help of or to the cell state. So what is the cell state? How we can able to represent the cell state? The new information can add to the cell state by creating a vector that is known as GT. And what is this GT? This GT is called as the new vector or candidate state or internal state vectors. So basically what exactly the importance of the cell state? The importance of the cell state is that we are updating the cell state by adding relevant information or we are deleting certain number of or certain informations. So the cell state information has to be updated each time. So this will help to decide that what information are to be kept or in memory, what information to be deleted from the memory. So this can be done by creating a new vector. And what is this vector? This vector is known as GT, which is known as the candidate state or that is known as the internal state vector at a time step that is equal to T. So now this candidate state is controlled by the tan hyperbolic in place of a sigmoid because the tan hyperbolic ranges between -1 to 1, which is either positive or negative, and sigmoid ranges from 0 to 1, that is always positive. So this is the reason that why we are using the tan h in candidate state, not in the sigmoid that means sigmoid. So if we look into the expression of the GT, which is the similar representation to that of the forget gate or the input gate or the output gate. In place of sigmoid, there is a tan h is situated here. So now, what is U? U is nothing but the weight that is associated with the input to the hidden. So G is representing to the candidate state or that is the internal state. So UG into XT plus WG into H of T minus 1, that is equal to the candidate state with multiplied with H of T minus 1 plus BG, that is the bias that is associated with the candidate gate. So the GT can be represented by tan hyperbolic U of G into XT plus W of G into H of T minus 1 plus BG. So this is the expression for this updating gate. So now how it will be updated? So this is the way how we can able to represent this update gate or that is called candidate state. So now the candidate state already as I have discussed, that is the tan hyperbolic U of G XT plus W of G H of T minus 1 plus BG, and that will be represented by these graphical representations. Now we'll just see the candidate gate, what exactly it will provide or what will be the output of the candidate gate. The candidate state holds all the new information that can be added to the memory. That means it basically contains the new information that will be added to the memory, whether the information in the candidate state is relevant or not. How do we decide whether to add or not to add a new information into the candidate state? That will be represented by GT. So that is equal to nothing but uh, the input get decide in adding the new information or not to the cell state. So now GT is multiplied with IT. So now if it is get multiplied with IT, the relevant information can be added into the candidate state. So what is GT multiplication with IT? The GT multiplication of with IT, the relevant information can be added with the memory. So if IT is equal to 0, the information not required. That means this output will become equal to 0. If IT is equal to 1, that means the information is required to update the cells. So that means why this GT is nothing but a tan h, because if GT is a tan h because it is ranging from -1 to 1, but we want the output to be present. But if we use a sigmoid, there will be a 0 is coming here. So that's why if IT is equal to 0, which is basically controlled by the sigmoid function, if it is 0, the information is not required. If IT is equal to 1, then the information is required. So that is the whole idea that how exactly it is working. So now just look at this diagram. It can be easily visible that IT is nothing but the input or input gate. So now what is IT? IT is equal to nothing but already we have discussed as per these previous equations. That means we can, sorry. So IT will be nothing but sigmoid of that is called ui of xt, then wi of h of t minus 1 plus bi. So now just look at this. So IT we can able to get. Similarly, GT we get. So GT is obtained by using the tan h function, and IT is obtained by the sigmoid function. Now GT is get multiplied with IT, because IT can be 0 or 1. If it is 0 means that means the information has to be removed. If it is 1 means the information has to be intact, or it has to be passed, or it has to be updated in the cell state. Now if IT is get multiplied with GT, that means what is GT? That is nothing but the cell, or it will provide the cell state information. That is a vector. So now this multiplication of IT with GT will update the cell state. So depending upon the value of IT, the cell state information can be updated, or it can be added, or it can be deleted. So this is IT GT already I have discussed. So adding the new information to the cell state. Now how to remove the information from the cell state? So this is from the previous cell state. Already we have discussed the forget get is basically responsible for removing the information. So what information is not required, that has to be removed from the forget get. So how it can be removed? So the information no longer required has to be removed. So already we know that what is the forget get output? The forget get output is nothing but it can be represented in the similar manner as per this equation, that is equal to nothing but, if I will write ft, that is equal to nothing but sigmoid, in place of tan we will write sigmoid u of f xt w of f h of t minus 1 plus b of f. So now just look at this representation. So now ft, already we know the expression for ft. Now this ft is get multiplied with the previous cell state, that is equal to c of t minus 1. So when it is ft is get multiplied with the previous cell state information, so what will be the output? This output is nothing but the cell state, that is equal to ct. So what is forget get? So forget get is nothing but used for removing the information that which is not required in the cell state. So how it can be removed? This can be removed by multiplying ft with the previous cell state informations. So multiplying the previous cell state and forget get information in the cell state can be written relevant information in the cell state. So how exactly it is returning the information? Now what is the update cell information? The update cell information is nothing but ct is equal to ft into c of t minus 1 plus it into gt. So what already we have discussed, it into gt. It into gt is basically responsible that which information is to be added, and which ft into g of t minus 1 basically responsible that which information to be forgot. So now by combining this information, that is ftc of t minus 1 and it into g of t, then the cell state information can be updated, and this is called the updating of the cell state by the help of, or in case of LSTM. Now how the output can be obtained? So already we have discussed that output get basically responsible to provide the output or to predict the output from the cell state. So that means the cell state information has to be used to provide or to predict the output. So what will be the output? This can be obtained, that is nothing but the HT, which is nothing but the updated hidden state information, that is OT. What is OT? OT is nothing but the output get or output to get information into tan of HCT. What is CT? CT is nothing but the cell state information. So now hidden state is used to compute the output, but how it can be computed in the output, that is nothing but HT is equal to OT tan of CT. So this is the CT, this is the previous C of T minus 1, that is nothing but the previous state informations. Now this CT is passed into the tan hyperbolic. This will give rise to tan CT. Now this tan CT, HCT is get multiplied with the OT to give rise to the updated hidden state information. So the output get is responsible for deciding what information should be taken from the cell state to give us the output. So the output can be represented as the YT of softmax of V of HT. So what is V? V is nothing but the weight that is associated with the hidden state to the output. So this YT can be predicted as softmax of V of HT. So the output get is responsible for deciding what information should be taken from the cell state to give us the output. So this diagram shows that how the LSTM gates are present. Already we have discussed there are three gates are present. One is the forget gate, which tells about what information to be forget. Now the next gate that we have discussed, that is called the IT, that is known as the input gate informations. So what information to be added? What's the information to be added? Next, what information to be output? That means what is the output gate? So now, what will be the next step? So just look at this diagram. Here there is a C of t minus 1, H of t minus 1. So now this H of t minus 1 is the previous state information. This is the XT. That is nothing but the input that is given to the LSTM unit at the time state t. So there are three LSTM units are present. One is called the LSTM unit 1, LSTM unit 2, and LSTM unit 3. So this LSTM is nothing but the LSTM unit at time instant t. This LSTM at t minus 1, this is nothing but t plus 1. Now what are the states or how the output is predicted? Just we'll summarize it here. So now this xt is taken, and this here is the previous h of t minus 1. And now what is the output ft? Already we have discussed the output of ft depends upon this input to the hidden state weight with this input, then hidden state to hidden state, and with the bias. So that will give rise to the ft. Now this ft is get multiplied with your c of t minus 1. So this will give rise to the output, what information to be deleted. So this output is nothing but what information is deleted. Now this xt by the help of the input gate will decide what information to be added. Now this is nothing but the IT. This IT is get multiplied with the output of tan h, that will provide the GT. So GT into IT will provide the this output, whether the input to be added or not. So now this GT, IT as well as FT into CT, they are combined and passed into the tan hyperbolic. So next, the output information of the output gate will pass, they will be get multiplied to give rise to the output state information. So this output is nothing but the output of the LSTM. So we can represent this by the help of the mathematical representations, which is summarized here. So if we look into the forward propagation of this LSTM network, the input gate, as we have discussed, IT is equal to the sigmoid of UIXT plus WIH of t minus 1 plus BI, whereas the forget gate is nothing but U of FXT plus W of FH of t minus 1 B of F, and the output gate is equal to U xt plus w h of t minus 1 plus bo, and the candidate state, which basically tells about the gt, as we have discussed here. This is gt information is coming here. Gt is get multiplied with it, that is nothing but the tan h ugxt plus wgh of t minus 1 plus bg. So in case of candidate gate, we are using the tan hyperbolic in place of sigmoid, because the tan hyperbolic will give rise to minus 1 to 1, and when it is get multiplied with the input, whether the information has to be passed or the information has to be deleted. That means whether it has to be updated or not. Now what is the cell state information? Already just look at this previous diagram. Here we are getting it into gt. Now this where I have kept the pointer, that is nothing but the ITGT. Now FT is get multiplied of C of t minus 1. Now this is FT into C of t minus 1. This FT into C of t minus 1 is get added with IT into GT. So this will give rise to this output. So now this output is represented by, that is the cell state, that is FT C of t minus 1 IT GT. So now what is the hidden state information? So now the hidden state information is coming to be, what will be the hidden state information? This hidden state information will be represented by OT of tan HCT. So what is OT? OT is nothing but the output of the output get output get information or expression that will be get multiplied with a tan hyperbolic CT. So now just look at this diagram. So in this case, this is OT. This is nothing but the current state, that is CT. So tan H CT. So tan HCT is get multiplied with OT. So this is coming to this output. So now this output is nothing but the HT or the hidden state information. Now this hidden state information is get multiplied with the weight that is associated with the hidden state to the output, that is nothing but VHT, and softmax is computed. So now what is the output? Just look at this expression diagram. So now the output that will be coming to be the sigmoid of this V into HT of the sigmoid functions. So this is exactly how this LSTM network is working by the help of the three gates. One is called the forget gate, input gate, and output gate. And in this case, we have discussed that how the information can be removed from the memory and how the new information can be added into the memory, as well as how the cell state information is updated. By this updating cell state information, this is passed into the next LSTM network, and this process will continue how it is happened in case of the recurrent neural network. So I hope it is clear to everyone that how this LSTM network basically working. So now we'll talk about that how to update these weights. Already we have discussed in the recurrent neural network how the weights have been updated, because we are calculating the total loss, and then after calculating the total loss, we are calculating the gradient of this loss with respect to u, with respect to w, as well as with respect to v. And the same similar manner, we have to calculate the weights with respect to u, w, and v. But as in this case, there are three gates are present. One is called the forget gate, output gate, as well as the input gate. So we have to look into the three things that means for the different gates. So now back propagation in LSTM tells about the loss is computed at each time step to find the operation of this LSTM network. And in this case, the cross entropy loss function has been calculated. That is LT is equal to minus YT logarithmic of Y caps. So actual output is equal to IT, and the predicted output is equal to Y hat. So the final loss is nothing but the summation of the loss, that is equal to Lj, j is equal to 0 to t. So in this case, there are t number of layers are present. So t number of layers will give rise to the total loss, that is equal to L. So now what is the criteria, or what is the steps to be followed to get the output? That means we have to optimize. So we have to minimize the loss using a gradient descent algorithm. So now the derivative has to be computed with respect to loss for the different weights. We have weights in the hidden to input to the hidden layer, hidden to the hidden layer, as well as hidden to the output layer. So input to the hidden layer, the weight is associated as u or named as u. Hidden to the hidden layer is that is weight is associated as w, and hidden to the output, that is the weight is known as the v. So now these three weights has been to be calculated for all the gates. So that means input to the hidden layer weight, hidden to the hidden layer weights, as well as hidden to the output layer weights. If we'll talk about the input to the hidden layer weights, there are for input gate that will be UI, forget gate that is UF, output gate that is UO, and candidate gate that is known as the UF. So similarly, the hidden to the hidden layer weights are represented as input gate, forget gate, output gate, as well as candidate gate. So that will be represented by WI, WF, WO, as well as so this is candidate gate. So here I made a mistake, that is this will be G, UG, not UF. So similarly, this is equal to WG, not WF. So now hidden to the output layer, that will be represented by this V. So now, what is the updating rule? The updating rule tells about the new weight, that is equal to weight minus the alpha, the derivative of the loss with respect to the weight. So this is the updating rule, or weights to the gradient descent, and observe the weights according to the updating rule criteria. So now, how the gradients with respect to the gates has to be computed. So this has to be computed for the LSTM cell and requires the gradients of the gates for the candidate state. So the gradient of the loss function with respect to the different gates and the different candidate state has to be computed. So that means we have to calculate the gradient of the loss with respect to the hidden state, with respect to the cell state, etc. So now, how to compute it? If we'll take the derivative of the sigmoid function, that can be represented as sigma x 1 minus sigma x. If we'll take the derivative of the tan hyperbolic x, that can be represented by 1 minus tan h square x, or hyperbolic square x. So now these two information has to be used in this LSTM network for simplification. So gradient of loss with respect to the hidden state and the cell state used for multiple times. So these two is used for multiple times. So gradient of loss with respect to the hidden state. What is the with respect to the hidden state? We know that the output that will be represented by the predicted output YT, that is nothing but the softmax of VHT. So what is V? V is nothing but the weight that is associated with the hidden state to the output, and HT is nothing but the hidden state information. So here we have substitute a variable that is equal to ZT in place of a VHT. So what is ZT? That is equal to VHT. So we have to compute the loss, the derivative of the loss with respect to ht. So if we'll apply the chain rule, del L by del zt, derivative of zt with respect to the ht. So now derivative of loss with respect to zt. So now substitute the zt as vht. So if we'll substitute as a derivative of vht with respect to ht, so this will give rise to v. So del derivative of loss with respect to zt. Already in yesterday's discussion, we have calculated what is del derivative of loss with respect to zt. That is nothing but y prediction minus y actual. That is the output prediction minus output actual into v. So gradient of loss with respect to cell state. So what is the cell state CT? How we can compute? We have to compute, or this can be calculated by taking the derivative of the loss with respect to the cell state. That is del L by del CT. So what is del derivative of loss with respect to del CT? That can be computed as derivative of loss with respect to del HT and derivative of HT with respect to del CT. So what is del HT? Already you know that the HT is equal to OT tan CT. Already we have discussed in case of LSTM equations. What are these LSTM equations? These are known as the LSTM equations. So now HT is equal to OT tan hyperbolic CT. So now we'll substitute this equation in this expression and calculate the derivative. So del of OT tan HCT, if we'll take the derivative and do the simplification, we can get a derivative of loss with respect to del HT into OT 1 minus tan square HCT. So already we know that the derivative of tan is equal to nothing but 1 minus tan square x, which is substituted in these expressions. Now the gradient of loss with respect to the output. So what is the loss, derivative of loss with respect to the output? The derivative of loss with respect to output can be computed as derivative loss with respect to HT, derivative of HT with respect to OT. So what is HT? HT is equal to nothing but OT tan CT. Already you know that. We'll just substitute it and we'll calculate the derivative. We can get del L or del HT of tan HCT. So similarly, the gradient of loss with respect to the input gate, that is known as the IT. So what is IT? So derivative of loss with respect to IT can be computed as derivative of loss with respect to CT. Why? Because we know that the cell state information depends upon the addition of what information is removed and what information is added. So this basically tells about what information has to be added into the cell state. This first term decides what information has to be removed from the cell state. So now CT is equal to FTC of T minus 1 plus IT into GT. So if we'll substitute the value of CT in this expression, that derivative of loss with respect to CT and derivative of that is equal to FT C of T minus 1 IT GT. So if we'll take the derivative of this part, this will give rise to GT. So this expression is known as the derivative of loss with respect to CT into GT. So gradient of loss with respect to the forget gate. So what is forget gate? So the forget gate basically tells what information to be forgotten. So the derivative of loss with respect to forget gate can be computed as derivative loss with respect to the candidate state, that is CT, derivative of CT with respect to the forget gate. So why it is CT? Because already we have discussed that CT is nothing but the next state output or the state output at the time instant t will be depending upon what information is forgotten and what information is retained. So the first part, as already we have discussed, this tells about what information to be forgotten, and the second part tells about what information to be added into the cell state. So now if you substitute the value of CT in this expression, that will be nothing but FTC of T minus 1 ITGT. So now if you take the derivative of this part, this will be nothing but C of T minus 1. I hope everybody knows the derivative and it can be easily computed. So gradient of loss with respect to the candidate set, that is equal to GT. So what is the candidate state? That means if you take the derivative of loss with respect to GT, that is the derivative of loss with respect to CT and derivative of CT with respect to GT. Already we have discussed CT is nothing but depends upon the two information, and what information has to be removed, what information has to be added. Now substitute this value or this expression and take the derivative. If we take the derivative of this will give rise to derivative, this will give rise to IT. So now derivative, so del of L with del GT will be represented by derivative of loss with respect to CT with multiplied with IT. So now what will be the gradients with respect to the weights? Already how it can be computed with respect to the different weights. So that means calculate the gradient of loss with respect to the hidden to hidden layer weights, that is equal to W for all gates as well as the candidate states. So already we know that the gradient of loss with respect to Wi, how it will be computed. So for that reason, we can write that is I stand for your the input gate. So IT information, that is the output of the input gate, can be represented as sigmoid of UI xt plus Wi h of t minus 1 plus Bi. What is U? U is nothing but the weight that is associated with the input to the hidden state, and xt is nothing but the input that is given at the time instant t. Wi is nothing but the weight that is associated with the input gate in hidden to hidden state, and h of t minus 1 the previous state information, and Bi is associated known as the bias. So del L of del Wi, that is the derivative of loss with respect to the weight associated with the input gate, can be represented as summation j is equal to 0 to t minus 1 del of Lj by del of Ij, and del of Ij with respect to del of Wi. So now substitute the value of Ij, that is equal to this value in this expression, and simplify this. We can reach out j is equal to 0 to t minus 1 del of Lj by del Ij into 1 minus j into h of j minus 1. So now what will be the gradient of loss with respect to Wf? Already you know what is Wf. Wf is nothing but the weight that is associated with the forget gate. And what is the weight that is your forget gate output expression? That is the sigma of ufxt plus Wf h of t minus 1 plus Bf. So now, if we calculate the loss, that is derivative of loss with respect to Wf, that is nothing but derivative of loss uh, with respect to f of j and f of j with respect to w of f. So now, yeah, if we substitute this value at here, this will reach out, or this will boils down to this expression. So this can be easily computed by the taking the chain rule of the derivative. So similarly, the gradient of loss with respect to output, that is the output gate, that is known as the output gate output, that is OT, the output gate information, that can be represented as sigmoid of u of O xt plus W of O h of t minus t minus 1 plus BO. So derivative loss with respect to W of that is the with respect to the gate that is associated with hidden to hidden state of the output gate, that can be represented by derivative of loss with respect to del of OJ, derivative that is equal to derivative of the output gate with respect to del W. So this is, if we simplify, this is the output that we are getting. So if we look at these three expressions, gradient loss with respect to Wi, gradient loss with respect to Wf, gradient loss with respect to Wo. So all these equations are almost similar. That means in this case, there is a input gate information is present, Ij into 1 minus Ij into h of j minus 1. In case of forget gate, it will be fj minus into 1 minus fj into h of j minus 1. In case of output gate, it will be nothing but oj into 1 minus oj into h of j minus 1. Now, what will happen in case of a gradient of loss with respect to the candidate state? So this candidate state can be computed by derivative of loss with respect to the candidate, that is del of g, and derivative of g with respect to del of w. So this will be simplified. It will be represented by del of lj, del of j, that is derivative of loss with respect to g, that is the candidate state, into 1 minus g j square into h of j minus 1. So this is the representation of the gradient of loss. So now we have to compute what is the gradient with respect to u. So what is u? U is nothing but the weight that is associated with the hidden state to the output state. So how we can able to compute the output? So in this case, we have to compute for the input gate, output gate, as well as the forget gate. So already we know that the IT, that is the expression for this input gate, is equal to sigmoid of ui xt plus wf h of t minus 1 plus bi. So derivative of loss with respect to this weight that is associated between the hidden state to the output will be represented as summation j is equal to 0 to t derivative of loss with respect to del ij and derivative of ij with respect to del u. So if we simplify this, so this will give rise to j is equal to 0 to t minus 1 derivative of Lj with respect to del of Ij into Ij 1 minus y, Ij into Xj. So in this expression and the previous expression, just look at here. In this case, Ij into 1 minus Ij into h of j minus 1, del Ij with respect to del Ij. So this is IT. So similarly, in this case also, we are getting with respect to ui, del of Ij by del Ij into 1 minus Ij xj. So this representation is similar. Similarly, gradient of loss with respect to the UF. The gradient of loss with respect to the UF can be computed as derivative of loss with respect to UF. That will be represented by this expression. That is equal to summation J is equal to 0 to T minus 1 del of Lj del of Fj. So that is equal to Fj 1 minus Fj into Xj. So if you look at this expression and the previous expression, that is equal to calculated with respect to Wf. So both have the similar in nature. This is the derivative of loss with respect to Wf. In this case, we are calculating the derivative of loss with respect to the UF. Similar, the gradient of loss with respect to the O. So or the that is equal to output get. So this can be computed as derivative of loss with respect to del u, that is equal to j is equal to 0 to t minus 1 del of lj, del of oj, and del of oj with respect to del of u. So if we compute simplify this will reach at this expression. So now if you look into the previous expression, how we have calculated with respect to the output that is called with respect to hidden state. So this is nothing but oj 1 minus oj h of j minus 1. So if you look into this expression, both are similar. So in this case, we are calculating the derivative loss with respect to the u. So similarly, the derivative or the gradient with respect to the gradient, that means ug, how it can be computed, that is the similar manner that we have computed previously. That is the derivative of loss with respect to uj, and this will be represented by this expression. So here we have calculated the gradient with respect to the different that means gates. So now there are certain questions. Just have a look into this, that what we have understood from this session's discussion. So how does this LSTM solve the vanishing gradient problem in case of problem that has occurred as in case of recurrent neural network? I hope this answer is known to us now after discussing the LSTM. What are the different gates that is associated with the LSTM and mention their functions? What exactly these different gates are used? What is the use of the cell state? Basically, the use of the cell state to decide that what will be the means information, what information has to be kept, what information has to be forgotten, and this cell state information is basically used to decide or the predict the output that already we have discussed. So here we'll talk about the gated recurrent unit. Basically, what are the limitations of the LSTM network? Then we can thought of this gated recurrent unit. If you look into the LSTM network, there are many number of gates are present. One is called the input gate, forget gate, and output gate. So there are too many number of parameters. So due to the many number of gates and states, so the back propagation in LSTM requires more parameters as well as more number of iterations, which leads to increase in training time. So this makes the LSTM network not to be practically used for many applications. So people's researchers thought of using GRU, that is gated recurrent unit. So what is this gated recurrent unit? It is a simplified version of this LSTM network. In case of LSTM network, there are three gates are present: forget gate, output gate, and input gate. But in case of GRU, there are two gates and one hidden state is present. So this is the advantages of this get recurrent unit, that how exactly it is advantageous over the LSTM networks. So here it is the LSTM network and it is the GRU network. I hope it is clear that what is the difference between both LSTM and GRU. So in this case, there are two gates and the hidden state and simplified versions of this LSTM. So what are the advantages of the GRU? So if you look into the advantages, it has a gated mechanism. What is a gated mechanism? So it uses a update gate and reset gate to control the flow of information. That means update gate basically decides what information to be updated here, and reset gate will decide what information has to be reset or to be removed or eliminated from the cell state. So this is used update gate and reset gate to control the flow of information. It can overcome the mitigating the vanishing gradient problems. So selectively allowing the relevant information to the gates prevent the gradients from vanishing. it has the improved memory management capability. That means effectively manage the flow of information. There is an update gate which controls the balance between keeping the past information and incorporating the newer information. So the update gate will keeps the balance between the past as well as the newer information. And it has a faster training time. GRU activation function can often be trained faster than that of this standard recurrent neural network or the LSTM networks. So now, as we have discussed, in case of a GRU, there are two gates are present. One is called the update gate, another is called the reset gate. Basically, already we have discussed that update gate basically update the information. What information has to be updated. So it decides what information from the previous time state can be forwarded to the next time state. That means it is the combination of the input and forget gate. And this update get information is regulated by a sigmoid transfer functions or sigmoid functions. So what is the update or what can be represented? That is equal to ZT. That will be represented by sigma uz xt plus wz h of t minus 1 plus bz, where uz represent the input to the hidden state. U always stand for input to the hidden state of the update gate, and wz basically represent the hidden to hidden weight information of the update gate, and B stand for the bias of the update gate. So Z basically represent the update gate symbols, and other variables are already we have discussed. Now, the second gate that is associated with the GRE, which is nothing but the reset gate. So what is the importance of the reset gate? Basically, the reset gate decides how to add new information to the memory, or we can say that how the much past information, that means the information which is not required, can be eliminated or to be forgotten. So this expression for the reset gate output can be represented by, that is the sigmoid function urxt plus wrh of t minus 1 plus br. What is this ur? Ur is nothing but the input to the hidden weight. As r stand for, this is nothing but the reset gate. xt is nothing but the input that is associated. W is nothing but the weight that is associated with the hidden to the hidden state. And R stand for the reset gate. BR is nothing but the bias that is associated with the reset gate. So in GRU, there are two gates are responsible for adjusting the state or flowing, or the basically controls the flow of information in case of a GRU. So now how we can able to update the hidden state? That means how basically the two gates, one is called the update gate, another is called the reset gate. These two gates are responsible for updating the information or transferring the information. How do the two gates help to update the hidden state? How new information is added to the hidden state? How to remove the unwanted information in case of the hidden state? So that things that we will discuss here, addition of new information to the hidden state. So how this new information can be added to the hidden state. So the reset gate is used for removing the informations. So which information has to be removed? Reset gate is used to create a content state for keeping the required information. So what is CT? So CT can be represented as that is a tan hyperbolic UCXT plus WCH of t minus 1 into R1. So now what is HT? HT is equal to nothing but 1 minus ZT into CT, ZT into H of t minus 1. YT is equal to nothing but the softmax out. So now this reset gate is used to create the content. So that is equal to CT. How the CT is content created by this expression. And HT already we have discussed, that is the previous hidden state, and YT is nothing but the predicted output in case of the GRU. Just look at these expressions. In case of GRU, we have the lesser number of equations. It makes the network to be faster compared to the LSTM. But if you look into the LSTM network, we have multiple number of equations and multiple number of iterations are present. So in this case, in case of a GRU, there is an update gate, reset gate, content state, as well as the hidden state, and which provides or leads to the output. If you look into the update gate, that will be ZT, which is represented by softmax UZXT plus WZ H of t minus 1. Already we have discussed this representation. Reset gate, that will be represented by RT, which is represented by obtained by the softmax URXT plus WR into H of t minus 1. Content state, that is CT, that is nothing but the passed into the tan hyperbolic UCXT plus WC into H of t minus 1 into RT. hidden state information that is equal to 1 minus zt into ct plus zt into h of t minus 1, and the output is equal to softmax that will be of v into ht, where v represent the weight that is associated with the hidden state to the output. So these are the three information that we have already, that is the information that we have discussed in case of LSTM. But if we compare these equations in terms of LSTM, so the GRU is much more faster. So now how the back propagation is possible in case of gated recurrent unit. So if you look into, as we have discussed, there are the total loss has to be calculated in case of the GR in back propagations. So the total loss is computed or can be calculated as the summation of j is equal to 0 to t Lj. So in this case, there are 0 to t number of layers are present. So the minimization of loss is found by computing the derivative of the weights. So as there are two layers are present, that means two gates are present. One is called the update gate as well as the reset gate. For update and reset gate, we have to compute the loss, that is the derivative of the loss with respect to the weights. So in case of input to the hidden layer weights is present, hidden to the hidden layer weight is present, as well as hidden to the output layer weight is present for both in case of update gate as well as the reset gate. So now, what is UZ? That is input to the hidden. That is nothing but UZ, UR and UC are present. That is corresponding to the update, reset and content weight. Similarly to the hidden layer, the weights that is associated as update, reset and content. And similarly, there is another that is hidden to the output layer weight is present, that is known as the V. So these weights have to be updated. These weights, that means the derivative has to be computed for the loss with respect to these weights to learning the weights. So now, the gradient of loss with respect to the hidden state can be computed as derivative of loss with respect to ht. That will be already computed previously. How it is computed already we have discussed. That is y hat yt hat minus yt into v. So gradient of loss with respect to the content state, that is equal to ct. So this can be calculated as derivative loss with respect to ct. That is sorry. So derivative of loss with respect to ht and derivative of ht with respect to the ct. So the chain rule is applied. Already you know what is the ht. Already this ht has been discussed in these expressions. Now this value of ht is substituted in this expression and calculated the derivative. So once the derivative is calculated, this equation boils down to these expressions. So again, if you simplify this, it can able to, this is the derivative of tan hyperbolic. So if you take the tan hyperbolic and simplify this expression, this derivative of loss with respect to ct can be computed by this expression. Similarly, the gradient of loss with respect to the reset state, that is equal to RT. So RT in the content state equations. So now how it can be applied? So again apply the chain rule. Derivative of loss with respect to RT, that is derivative of loss with respect to CT, and derivative of CT with respect to RT. So already you know what is the CT expression. Already you have calculated in case of this CT, that is equal to tan U of C xt double of C into H of t minus 1 RT. So now just substitute this value of CT in this expression. So and simplify this expression. So if you simplify this expression, we'll reach at this expression, that is derivative of loss with respect to CT. So then the gradient of loss with respect to the update gate, that is equal to ZT. So derivative of loss with respect to ZT, that is a derivative of loss with respect to HT, and derivative of HT with respect to ZT. So already we know what is that HT in the previous that is equal to 1 minus zt into ct, zt into h of t minus 1. This value is substituted in this expression and calculate the derivative, and this will boils down to this simplified expression. So now we have to calculate the gradient with respect to w and gradient with respect to the v. So if we calculate the gradient with respect to v, so that will be nothing but with respect to the hidden state, that is derivative of loss with respect to v, which will be represented as j equal to 1 to the total number of that is called time steps are present, or the layers are present, that is yj hat minus yj into h of j. So now the gradient of with respect to w has to be computed. So there are three w's are present. One is called wr, wz as well as wc. So now we have to calculate the gradient of loss with respect to wr. So how it will be computed? Thus w of that is a derivative of loss with respect to del r, that will be equal to summation j equal to 0 to t minus 1, double of derivative of loss with respect to r and derivative of r with respect to wr. So now substitute this value and you can able to get this expression. Similarly, the gradient of loss with respect to wz, so that will be represented by del of L by del of wz. So if you apply the chain rule, again derivative of loss with respect to z and derivative of z with respect to w. Already we know what is z, so just substitute this expression, we can able to get this expression. So similarly, Ct we know this is the value, so derivative of loss with respect to the Wc can be computed as derivative of loss with respect to C content and derivative of content with respect to the weights, and simplify the expression will reach out this expression. So in this way, how we can able to calculate the gradients with respect to the different weights. So similar the gradient with respect to the U. How to calculate the U? What is U? U is nothing but the weight that is associated with the hidden state to the output. Sorry, input to the hidden weight. So U is nothing but the input to the hidden weight. So for all the gates and the content state, we have to calculate what is the derivative of loss with respect to U. So as U is nothing but the input to the hidden weight. So and there are three things we have to calculate. That is the derivative of loss with respect to the UR, derivative of loss with respect to the uz, and derivative of loss with respect to the c. So just to substitute the value the similar way how we have computed with respect to the lr, the same way it has to be computed. So now we just look into what are the things that we have discussed today. We have discussed about what are the limitations of recurrent neural network and how these limitations can be addressed by the help of the LSTM. We have discussed what are the limitations of the LSTM and how this can be addressed by the gated recurrent unit. Now we'll look into the advantages and disadvantages of a gated recurrent unit. Already we have discussed this gated recurrent unit have the lesser number of gates, which makes the network to be faster. That means it has a faster training as well as efficiency, and it has a simpler architecture, consists of fewer number of parameters compared to the LSTM network. It is very effective in case of sequential task. What is sequential task? Basically, whenever we are looking into the time series data or the speech data, ECG or EMG data, basically this network will be effective to handle a long-term dependencies in a sequential data, like a language time series, and less prone to gradient problems. So that means it has a lesser problem with respect to the gradient. So if you look into the other side of this gated recurrent unit, it is a less powerful gating mechanism, limit their ability to capture a complex relationship or a long-term dependencies in certain scenarios. It has a potential for overfitting because more susceptible to overfitting, especially a smaller data set. It has a limited interpretability. That means it is just behaves like a black box to tell. That means what exactly the interpretation or explainability for this. So if you look into the application part of this GRU, then it is used in case of machine translation, text summarization, chat box used for building chat box that can be used for context of a conversion of a response in a natural way, or it can be used for sentiment analysis, whether positive, negative, or neutral. So already this is discussed. I'm not going through this. This already it is discussed. So these are the few references. So if you have any questions, please ask. We can have a discussion. So if you look into the discussion part, what we have discussed, we have started our journey with respect to a recurrent neural network, which is different from this deep neural network. In this case, it has a rolled over is present in case of the hidden state. And this recurrent neural network can able to predict the previous, that means predict the output based on the previous content of the hidden state. And this recurrent neural network has a limitation of a vanishing gradient, exploding gradient. This limitation can be overcome by the help of the LSTM. And the LSTM is having the three gates. One is the forget gate, output gate, and input gate. Based on these gates, it has to tell what information to be forgotten, what information to be kept. So LSTM is consists of multiple number of gates, which makes the network to be very complex, and it requires more training time. So in order to overcome that type of difficulty, researchers thought of using a reduced number of gates, that is update gate and reset gate, as in case of GRU, to update the weights. So this is all about this recurrent neural network. I hope I came to the end of the time. It's the right time to stop. If you have any queries, please feel free to ask. So there is some chat. I hope there is no more charts. Yes. Madam, sir, am I audible?
Yes, sir, we can hear you.
Yeah. So, any questions from the audiences?
Sir, as of now, I didn't receive any questions, sir.
Pardon? Okay, thank you. So, madam, then we can stop it here.
Yes, sir, sure, sir.
Thank
you,
you,
sir.
ma'am. Thank you, ma'am.
Thank you so much, sir. Thank you, sir, for your detailed session on optimization strategies for deep learning models. The insights into training efficiency and AI model fine-tuning have been incredibly valuable for our understanding of high-performance AI systems in medical applications. Participants will meet back at 4 p.m. Stay on the meet. The sessions will start at 4 p.m.
So, participants, I hope you have all completed the assessment. Yeah, the feedback link will be shared now. Just to inform you that we will not be taking that ATL thing into consideration. This assessment mark will only be taken into consideration. And just to inform you again that the assessment has been conducted, minimum 80% of attendance and 70% of marks in this assessment is required to obtain the certificate. And we will also be sharing the proof session recording in YouTube for monitoring the attendance. And we all request you to maintain minimum 80% of attendance. So we will be sharing the feedback screen now. There are two feedback forms that you have to fill. The one that we will be posting now, and also the one that is there in the feed ATL official page. Please do fill both the feedback forms. The ATL one is important as well as this one, because with the feedback form that we are posting only, we will be able to calculate your attendance. It is 7:30 already, and the test responses will be closed now. Participants, the feedback link is being shown on the screen. I repeat, please fill this feedback form and the one in the Atal official website also, because with this only we will be able to monitor your attendance. The feedback form is being shared on the screen and also it has been posted in the chat.
Hope every participants has filled the feedback form. We came to the end of the session. On behalf of Taraja College of Engineering and the coordinators, Dr. P. Chandrakumar sir, Dr. M.S. Sasirekha ma'am, and Professor R. Saraswati Meena ma'am, I take this opportunity to express a heartfelt gratitude to everyone who has contributed to the success of this faculty development program. First and foremost, we extend our sincere thanks to our Honorable Chairman, K. Hari Tyagarajan sir, respected Principal Dr. L. Ashok Kumar sir, and esteemed Head of the Department of Applied Mathematics and Computational Science, Dr. Parthasarathi sir, for their continuous support and encouragement. Your guidance have been helpful in making this FTP a success. We are deeply grateful to our renowned speakers and resource persons who have generously shared their expertise, research insights, and industry experience with us. Your engaging sessions provided knowledge and have truly enhanced our understanding of AI applications in medical data processing. A special thanks to our internal faculty members, research scholars, and technical staff who have worked tirelessly behind the scenes to ensure the smooth execution of this FTP. Your dedication and hard work are truly commendable. Finally, a big thank you to all our enthusiastic participants who have actively engaged in discussions, asking insightful questions, and made this program an interactive and enriching learning experience. Your participation has added immense value to this FTP, and we sincerely hope that the knowledge gained here will be beneficial in your academic and professional pursuits. Once again, thank you all for contributions, and we look forward to many more such collaborative learning opportunities in the future. With that, we now conclude our faculty development program, wishing you all the best in your future endeavors. Thank you.